Hello everyone, today I will present my final project of pattern recognition class. My topic is analysis of methods of recognizing patterns of programs to enable accurate sampling microarchitecture simulation. Let's see the goal of my presentation. First, I will introduce the microarchitecture simulation and sampling simulation. Then I will present how to represent features of code and programs. Then I will go through how to recognize the patterns by the program's features. Finally, we discuss the implementation and evaluation issues. At last, I will show you a demo. So, first, I will introduce the microarchitecture simulation. I will introduce what is microarchitecture simulation and what is sampling simulation and why we need sampling simulation. The microarchitecture simulation, in making a microarchitecture design decision, it is not very easy because the designer needs to consider many circumstances and also should make trade-offs. And making decisions without implement these solutions and comparing them with each other is also not possible. But implement all the solutions on chip is also not possible because it's time consuming and expensive. So the researchers and designers are trying to use software to keep machine states and thus simulate a machine which could run in certain workloads inside it and predict the results. Due to the flexibility of software that make change of the design solution is pretty easy. You only need to simply rewrite some configurations. So the sampling simulation, as the name says, is it fast forward the most part of the workload and only simulates a small subset of the workloads. The workloads are typically be the benchmark programs. The samples need to be able to represent the overall features of the original program. The evaluation metrics gained from these samples should keep low error rate comparing to the true value. The most famous sampling simulation solution is called SimPong, designed by UCSD. So why we need sampling simulation? The simulated machine, which is virtualized by software, cannot run as fast as hardware implemented machine, and typically the benchmark programs are also usually contains large and complex computation work. In spec 2006 CPU benchmark source, the most benchmarks contains 50 billion to 10 trillion ARM instructions. In Geom5 simulator, fast forward could perform at rates about 3 million instructions per second, but simulate with details to count the evaluation metrics in each cycle makes the simulation be 10 times slower, resulting in simulation to be finished in years. So that does not make sense. And also currently the benchmarks and simulators are not implemented in parallelized ways. That's the reasons why we need peak samples. So the possibility of picking samples and recognize the patterns of codes is that code are regular. And loops are the most weighted part of the programs, especially for the programs with long execution time. Uh, so in a loop, each iteration has the same architectural behavior, and the only difference is data in the register value is different. So one iteration could represent other iterations that makes sampling be possible. But in real-world benchmark programs, the control flow is more complicated than we previously discussed, and the features representation and pattern recognition will become slightly different. First, let's talk about how to represent features of program. We will first introduce the definition of basic blocks. The basic blocks is defined as the instructions between two branch instructions. So inside the basic block, the instruction could only execute one by one, and no control flow instructions inside the basic blocks. And then I will introduce what is a basic block vector. It's a high dimension vector. Each dimension represents the times of corresponding basic blocks executed and multiplies the instructions inside that basic block. The Euclidean distance between two basic block vectors represents the similarity of them. In represent the feature of programs, we first partitioning the programs into many intervals. Each has its own basic block vector, and using clustering method to find the samples we need. Here's a result of extraction of basic block vector in Gen5 simulator. For the clustering method, the k-means perform better in this problem than the hierarchical clustering as we set the experiment, because the picking samples means gaining the midpoint of each clusters. So the k-mean is easy to find the midpoint of each cluster. And also the hierarchical clustering focuses on partial features, but we need overall accuracy. Finally, the hierarchical clustering has high computation complexity comparing to k-means. This figure shows using the original SimPont frameworks to gain the basic block vectors. The original SimPont framework choose k-mean as the clustering method, and we will use IPC error rate as metrics to evaluate the clustering performance. The calculation of IPC sampling IPC error, sample IPC is shown as this equation, and this table shows the IPC error rate gained from k-means clustering and also two other kind of hierarchical clustering. One is from bottom to the top, and another is from top to the bottom. As we can see, the k-mean keeps average lower error rate. So before the clustering of k-mean, the original SimPont also do another work is reducing the dimension of the basic block vector. The dimension of basic block vectors are usually 1,000 to 50,000, which is pretty high and suffers a lot from curse of dimensionality. SimPont use random projection to reduce the dimension to 15. In this problem, we set up experiments and find that pre-simple component analysis has better quality, also has higher computation complexity. But comparing to simulation time, the reducing dimensionality and clustering overhead is negligible. Finally, we use the PCA via k-means as a method to recognize uh, the patterns of programs and implement it by modifying simple framework. Here are the results of the original framework and our modified version of framework. As we can see, our design has average lower error rate. And finally, I will show you a demo. I have put all the command lines that we need in this project to save more time. First, we need to extract the features by the Gene5 simulator, which means we need to use it to get the basic block vectors of all the intervals in the program. We use this command. We save our output to this directory, and we use 10,000 instructions as the interval length. So we goes to the output directory. Here's a GZ file, which is the profiling of the basic block vectors. We need to go to this directory. Is here, and we extract it to the SimPont framework directories here under the input directory. Then we go to SimPont, that modified version of SimPont. So then we use this command, which means which means we load these basic block vectors and use max 30 as keys, and save the SimPont as with file into these two directories. So as we can see, the SimPont and wait file has been saved. So we goes to the output directory and copy these two file back into the root directory of Gene5 simulator, and then we go back to the Gene5 simulator. First, I will show you how to do the full simulation using this command. We save the output to the another directory, and we use detail type CPU. And these are the cache configurations. As we can see, it's pretty slower than the previous simulation because that's fast forward mode. And for the real benchmarks, the simulation could be extremely long time, but in this demo I only show you a small program of matrix multiplication instance. It takes like 1 minute to finish. So we goes to the output directory. Here's a statistical file. We could gain the IPC overall IPC using this command. Here are the two results. Both of them are same because there are only one thread in this program. So these are the IPC true value we need, and I will show you how to gain the sample simulation result. As we can see, we saved the simpont as WAIS file here, and now we need to create a checkpoint before each simpont using this command. We save our results also in the output directory we previously used, and we use this simpont file, this wait file, and 10,000 instructions intervals and 10,000 instructions to warm up the cache. And we also use atomic CPU, which means fast forward all the instructions and save all the memory state and stack before each simpont. So here's the simulation process that saves the checkpoint. So we goes to the output directory again. As we can see, here are some checkpoint files. So then we go back to the root directory of GeneFi Simulator. I will show you how to gain the sample simulation result. We use these instructions, all the cache configuration are the same, but we use the checkpoint directory of the directory we previously saved the checkpoints, and also we restore the first checkpoint for simulation. So we goes to the sample simulation output directory, which is sample. Here's another statistical file. We also trying to find the IPC. The first is not the first two values are not we really need because they are the statistical before the real they are the statistical of warm-up period. So we need these are the values we really need. And this command means we restore the first simpont checkpoint, and here are 5 checkpoints. We need retake them separately, like go back to the root directory and use this command. We need to gain all the checkpoints and write down all the IPC values we need, because we need to calculate the sampled IPC by the equation we previously mentioned manually. So here's my demo, and thanks for watching my presentation.